Let's get to where we are. We skipped through all this stuff. We talked about what a CPC is, so this is kind of where we stopped. So just to review very quickly, a CPC, as we know, well, let's come here, is the ideal concentrator in 2 dimensions, where the concentration factor, which is the ratio of the input aperture divided by the output aperture, which is this input divided by this output, is 1 over sine theta, where theta is the acceptance angle. So we can see that if we want to concentrate the light more, we have to reduce the acceptance angle. In other words, we will have to track the sun more accurately. Okay, so that's a very fundamental trade-off. Now, today, what I want to, we also saw from here that in order to increase the concentration factor and reduce the acceptance angle, we have to increase the height of the CPC as well. So it's a simple geometry. But today, we also talked about 3D. Today, I want to focus a little bit on the properties of the CPC and gain some additional insight into this. Today's lecture might be a little bit, and also at the end, go look at a few examples and brainstorm some example design problems. So give you some taste for what is possible and some ideas. Today's lecture will be a little bit shorter than usual, but hopefully that means we have time at the end where Apratim will lead a brainstorming session on the design problems that I'll pose at the end. Okay, so well, let's jump right in. So we want to analyze the CPC from a perspective of thermodynamics, because we want to now, previously we looked at it from a geometry point of view. Now we want to analyze it from thermodynamics, and we will come to the same conclusion, but what we want to understand is the methodology afforded by thermodynamics, and also the fact that the geometry and the thermodynamics gives the same result implies a very important conclusion that the CPC is an ideal concentrator, at least in 2 dimensions. Okay, so we'll come to this conclusion. So that's at the end of this analysis. So we mentioned the CPC maximizes concentration. So that's what we want to show. To show this, let's consider a very simple example. Okay, let's imagine there's a cylindrical black body, which is shown here. Okay, it's a cylinder, infinitely long, so very, very long. It's at a temperature T, and let's say it's sitting in vacuum of space at 0 Kelvin. Okay, of course, this is a one-dimensional, right? So it's a cylinder. So we can consider, first of all, a unit length of the cylinder. Let's call it Lu is equal to 1. Okay, so that's what we will consider for now. The radius of the cylinder is small r, so we have the cylinder. Now it's a black body, of course, so it's going to emit radiation in all directions, right, cylindrically. And the flux emitted by this black body is given by the Stefan-Boltzmann Law, right? Sigma multiplied by temperature raised to 4 multiplied by the area of the black body. Now, we are going to consider a small area of the cylinder, so that's why we're going to call it dA. So the flux emitted by this cylinder in a cylindrical wave is basically sigma T raised to 4 times dA. Now, let's assume a length Lu. Okay, and we're going to set it to 1 shortly, but let's assume it's Lu. Then dA becomes 2 pi r Lu, right? That is the surface area of a cylinder. So 2 pi r is the circumference multiplied by Lu gives us the surface area of the cylinder. So it's dA can be replaced now by 2 pi r times Lu times sigma T raised to 4. So that's now the flux. Now we're going to look at the flux emitted per unit length. So we're going to set Lu equal to 1. So then the flux becomes 2 pi r sigma T raised to 4. Okay. So far so good, because it's simple. So we have a cylindrical black body of radius r, and it's emitting flux given by sigma T raised to 4 multiplied by the area of the surface area of that cylinder, 2 pi r, because it's unit length. Okay. Now this radiation is now being intercepted over here by one-dimensional CPC, okay, or two-dimensional CPC, sorry. In other words, it's a CPC which looks like that. Let's not call it a CPC, let's call it a concentrator, because it doesn't need to be a CPC. We're going to just make it some sort of concentrator, which is two-dimensional, which means that in the third dimension, it's infinitely the same, right? It's infinitely long and it's uniform. So it has some shape like that. And we'll call it a linear concentrator with a concentration factor of C. And that concentrator is going to intercept some portion of the flux that is emitted by here. And of course, the portion of the flux is emitted by here that is intercepted by this concentrator is dependent upon this distance, like how far away is the concentrator from the source, and what is the area of this concentrator, right? Because the flux from here is emitted all over, right, in a huge circle. And that's what we will analyze next. So we're going to take a cross-section of this three-dimensional picture. We're going to take a slice through it, okay, which is shown here. So here we have our source, we call it SR, temperature T, radius R. And at a distance d, small d away, we have our concentrator here. Okay. It's a linear concentrator, so it looks like that. There's an input aperture of A1, output aperture of A2, and theta is the angle that is subtended by the edge ray, right, on the concentrator, just like before. So the amount of radiation the entrance aperture A1 receives per unit length, so we know there's a flux that's emitted per unit length from the source. What is intercepted by this concentrator is what is spread across this large cylinder, right, of radius d, that is in the denominator. And you have to, in the numerator, multiply it by the area of the entrance area of this concentrator. So that's a fraction that is intercepted by the concentrator. So you take A1, which is this length in this direction, times a unit length. So we're going to look at unit length. So in the direction out of plane of the screen, we're going to assume the length is 1. So the area of this concentrator is now A1 times 1. So that goes in the numerator. In the denominator, we get 2 pi times d. Okay, 2 pi times d is simply this big surface area multiplied by 1 in the direction perpendicular out of the plane of the screen. So this fraction, A1 divided by 2 pi times d, is the fraction of the energy or the flux that is intercepted by the concentrator. The total flux emitted, of course, the same as before, just like in the last slide, which is 2 pi r, which is of the source. R is the radius of the source, multiplied by sigma t raised to 4. So we put them together, we get the flux that is intercepted by this concentrator at every unit length. Now we are going to assume that there is a black body that absorbs this radiation of the exit aperture A2, okay, like a solar cell, for instance, okay. Now, of course, this black body is going to be at some temperature that is less than T, right, because it's absorbing the energy. But slowly so it absorbs the energy, it's going to build up, it's going to increase its temperature until a thermal equilibrium between this black body here and this source here is reached. Everything, assume there's nothing else in the universe, okay? This is 0 Kelvin. So of course they have to reach a thermal equilibrium because this is going to absorb the heat energy until it reaches the same temperature. So once it reaches the same temperature, of course this is a black body, so it's going to emit as well. It's going to emit in all directions. And the flux it'll emit will be given also by the Stefan-Boltzmann law, and let's call it phi 2, which is sigma A2 times T raised to 4. A2 is the area, of course, here, times 1. We're going to ignore that 1 because it's a unit length, of course. Sigma A2 times T raised to 4. Now, because it's thermal equilibrium, of course, any flux that is emitted from here, intercepted by this concentrator, must be the same as the flux that is emitted by the source. Here we're going to assume that the source is going to emit only back, to the left, not to the right. There's nothing there to emit it to, right? There's nothing to absorb there, so it doesn't make any sense. So we're going to equate those. Then what we get is a very simple expression. Sigma t raised to 4, 2 pi r over 2 pi d times a1 equals to sigma a2 times t raised to 4. And if you write this out, everything cancels out. All the sigmas cancel out, t cancels out. It's the same temperature, 2 pi's cancel out, of course. So you end up with a1 times r over d equals a2, or a2 equals a1 times sine theta. Now r over d, of course, if you look at sine theta, that is exactly r divided by d. Okay? Because that's the tangential ray from the edge of the source. So we get the exact same expression as we derived before, but of course before we derived it using simple geometry, right? Because it was a function of the parabola, if you remember. Here we're deriving the exact same expression from purely thermodynamics. And we have made no assumptions as to the shape of the concentrator. This is very, very important because we end up with the same expression without making no assumption on the geometry of the concentrator. And we know that this condition is held for the CPC. So the only conclusion we can draw now is that the CPC provides the thermodynamically ideal or best concentration that is possible. Okay, so just to drive home that point, since the rest of the space is at 0 Kelvin, radiation leaving A1, which is this entrance of this concentrator, and coming from A2 can only be headed to the source because there's nothing else in this particular universe. This implies that the acceptance angle of the CPC with entrance aperture A1 cannot be larger than theta, right? So exactly the same things. In other words, any radiation that is escaping from A1, there's nowhere else it can go other than this source. So the largest extreme ray that will escape from here is the edge ray here, the acceptance angle of theta. So we can also think about it in the situation where the source becomes really far away. So D becomes close to infinity, then for a constant theta, because then we only deal with parallel rays as we saw in the last lecture, and theta becomes, so we have a constant theta that we need to consider. And R becomes large, but that's not so important because D and R both increase at the same rate, so theta is constant. What that means is that this now, instead of being a large circle, becomes essentially so large that this becomes a straight line. So we lose the curvature here. Okay, then we see that A1 is simply not a curve, it just becomes a straight line, same as A2. And then we can very easily say the concentration factor is simply A1 divided by A2, and that is 1 over sin theta. So here we come to the conclusion that thermodynamically, this is the maximum possible concentration in 2 dimensions, because we are simply deriving this from the first law of thermodynamics and thermal equilibrium. Of course, we know this from the last lecture is the same as the CPC. So the logical conclusion, so the CPC gives the maximum possible concentration in 2D of all possible shapes. Okay, so it's a bit of a roundabout argument, but basically we are showing here, at least qualitatively. So it's not a purely rigorous argument if you go through it super carefully, but basically come to the conclusion the CPC is the best you can hope to do. So in other words, if you try to start designing other types of concentrators, let's say because the CPC is too tall or it's too heavy or whatever, then we need to understand the best we can hope to do is what can be done with the CPC. So any other design, you should really try to get the performance as close to that afforded by a CPC as possible. So it's kind of an ideal situation when you think about your design problems. So, so that was the case for 2 dimensions. We can do the same type of analysis in 3 dimensions as well. Of course, in this case, instead of the source being a cylinder, now we have the source as a sphere. So it's a big sphere here, radius r, like the sun, for instance, at some temperature T. And then we still have a concentrator here. So it's drawn sort of like a paraboloid, but it's not important what the shape is for this argument. Here we will see that we have to deal with something called a solid angle, which we will come back to later on when we talk about other types of concentrators. But in this situation, we'll think about the extreme rays. So you have the extreme rays in one plane and the extreme rays in the orthogonal plane, and both acceptance angle, the whole acceptance angles in this case, theta. The area of the entrance aperture is A1, area of the exit aperture is A2, so the concentration factor is A1 divided by A2. We can still take a cross-section through here, through the center of the sphere, and you end up with a picture which looks exactly like before, right? We have the radius r here, the distance d here, the theta here, defined as sine theta is r over d. And basically, we can come up with the same expressions. The flux emitted by the spherical source now is, of course, the area of the sphere, which is 4 pi r squared. Okay, that's the surface area of the sphere, times sigma t raised to 4, which is the Stefan-Boltzmann Law. Area times sigma t raised to 4. The radiation captured here is simply this total flux divided by the fractional area of the entrance aperture of this three-dimensional concentrator relative to the full large sphere over which the flux is distributed. Right? So that is A1 divided by 4 pi d squared, of course this distance being d. So total flux multiplied by the fractional area that is intercepted, which is this big A1 divided by 4 pi d squared. So of course you cancel all these out. So the point, of course, is that this will get concentrated onto a black body at the exit aperture A2, just like before. And at thermal equilibrium, this black body heats up to a temperature T. So this black body here, which is, let's say, a solar cell, is the same as that of the source, the sun. And the radiation that A2 emits, because the black body must equal that it receives. So A2 emits with an flux, which looks like that, area, A2 times sigma T raised to 4, and it should equal this intercepted flux by this concentrator from the source, which is this equation here. And again, you can cancel things, most of these things out, and you get a very relatively simple expression where A1 over A2 is D over R squared. Of course, A1 over A2, we know, is the geometric concentration factor, the area of the entrance aperture divided by the area of the exit aperture. And A1 over A2 is 1, D over R is simply, R over D is simply sine theta. So you can replace that. So A1 over A2 is 1 over sine squared theta. Okay. And just like we did in the two-dimensional case, if you make the source really, really far away and theta is maintained, then this, instead of being a curve here, A1, it becomes a straight line because this circle now becomes so huge. Okay, so in the limit, it becomes a straight line. And then we can simply say this is you don't need to worry about this curvature here. So it makes it simpler in terms of analysis, A1 over A2. And what's critical here, of course, now we see that the concentration factor is not just 1 over sine theta in 3 dimensions, it's 1 over sine squared theta. So of course that means if you build a concentrator that's in 3 dimensions, you get much higher concentration factor for the same acceptance angle. Okay, so of course that is common sense, but we can actually quantify it with that expression. So so just be clear that in 2 dimensions we had this expression. Concentration factor is 1 over sine theta, where theta is the acceptance angle. But in 3 dimensions, the concentration factor is 1 over sine squared theta. So important distinction. There's one other thing we can do when we do concentration, which is to immerse the black body in a medium that is higher refractive index. So if the black body is immersed inside the concentrator whose refractive index is n, and we'll see what this means shortly, but imagine that the concentrator is made up of some material with a refractive index n, and that's index matched with the black body. So the black body is also refractive index n. Then we need to account for this. This comes out because the sigma that we talked about as a constant is a fairly complicated expression here, but all of these things are constants except for the n. this sigma turns out to be proportional to the square of the refractive index of the material of the black body. In other words, we can write the sigma as n squared times the Stefan-Boltzmann constant in vacuum, which is sigma v, which is all this stuff here, which we can ignore for now because these are all constants. C naught is the speed of light, h is the Planck constant, k is the 2 pi over lambda, depends on wavelength, of course. But we're going to talk about a single wavelength at the moment, so we're going to treat this as a constant. Okay, so here gives us a very interesting opportunity to increase the concentration factor, as you will see. Now, what's different here in this situation is that, remember, the source is still in vacuum. Okay, this is still immersed in vacuum. The black body of the receiver or the solar cell is now immersed in some refractive index n. So there is an asymmetry there, which results in this expression, which is the same equation as before, where the flux emitted by the source, of course, is sigma v, which is the vacuum. This is the same expression as before, except that we replace sigma by sigma v, which is the vacuum Stefan-Boltzmann constant. And this is a1 over 4 pi d squared is the intercepted flux that is equal to now the flux that is emitted by the receiver, which is A2 times n squared sigma v times 0 to 4. So only difference is the fact that we have an additional n squared here because of the higher refractive index material of the receiver or the black body. Now, if you look at the concentration factor, A1 over A2, it becomes n squared divided by sine squared theta. So this is actually quite interesting because it allows one to simply, by immersing the black body of the receiver, the solar cell, for instance, in a material of refractive index n, you can increase the concentration factor by a factor of n squared, which can be a big deal, right? Because the refractive index, for instance, silicon is about 3, which means that n squared will become roughly 9, right? 3 squared. So you can increase the concentration factor by a factor of 9, which is a huge deal for the same acceptance angle. In 2D, this we can prove this general result essentially as what you would expect. A1 over A2 is n over sine theta. Okay, so you get an advantage, a factor of an additional n. We can think about this from geometrical optics as well. And it's easy to do this by looking at a, let's say, solid CPC, where it is made up of some material of refractive index n. And of course, outside is vacuum or air. Let's follow a ray as it enters. The acceptance angle, half acceptance angle is theta, the full acceptance angle is 2 theta. So if you look at this ray, of course, it has to undergo Snell's law, refraction, right? So it in this case, because the index n is greater than 1, is going to bend towards the normal, as we know. So the angle of refraction here, theta star, is a little bit less than theta, right? And the design of the CPC is such that the edge ray here needs to end up at this point here, right? Or somewhere in the receiver. Actually, the edge ray at the very edge will end up here, of course, but in between it has to end up somewhere here. It doesn't need to be at the edge, of course, as you know by now. What's critical, as you can see, is that outside the air, you have an acceptance angle of 2 theta, full acceptance angle, but inside the CPC, the full acceptance angle is 2 theta star, which is a little bit less. Okay, and that gives you the idea of increased concentration factor. Now you can easily write this. Sine theta is n times sine theta star from Snell's law. And we know that this A2 over A1, excuse me, A1 over A2 is 1 over sine theta star, because that's the angle inside the CPC, okay, which we derived before. Now we can simply write the sine theta star is 1 over n times sine theta, so A1 over A2 becomes n over sine theta. So we can also prove this from simple geometrical optics as well. Okay, so of course this is a very interesting and useful thing, which means that if you immerse your solar cell, which will sit here, in some material that can be index matched to some higher refractive index material that makes up the CPC, you can increase the concentration factor, which can be a big deal because increasing the concentration factor can increase not only the total power output, but potentially increase the efficiency of the solar cell as well. It depends on the material, but for instance, for many of the 3-5 materials, this can be done. So I'll kind of point out an very important paper which came out in Nature in 1989, so a while ago, which basically showed, its title is Concentration of Sunlight to Solar Surface Levels Using Non-Imaging Optics. So basically they used a non-imaging design, optical design, and by immersing the measuring device in high refractive index material, they were able to create a temperature that is equivalent or slightly higher than the temperature of the surface of the sun, which of course sounds crazy. So that's why it was published in Nature. And the person who published this paper, Roland Winston, is considered the father of non-imaging optics. He's one of the early pioneers in this field at the University of Chicago. So in other words, to think about it, this was a way of producing irradiance on Earth. Irradiance, if you remember, is the intensity or watts per meter squared that exceeds that on the sun's surface. So this is the typo. It should be sun. And their system is relatively simple to understand. So sunlight comes in. There is a primary concentrator, which is kind of like a parabolic reflector shown here. So it's a two-dimensional parabolic, three-dimensional parabolic reflector. And it concentrates onto a non-imaging secondary concentrator like a CPC. So this is an approximation to a CPC. And of course, the acceptance angles for this secondary concentrator is whole acceptance angle is 2π in this case. So of course, this input acceptance angle is very small, right? They're only accepting the parallel rays here. So that's an important consideration, which is how they can get very, very, very high concentration. In this case, the overall concentration factor is over 10,000. And they have what's called a calorimeter to measure the temperature, which is shown in magnified view here. So the light comes in. They basically have this concentrator. They call it a lens, but it's basically a modified CPC. An image of the sun is formed, of course, and because this parabolic reflective concentrator does that. And they have an oil-filled silver vessel into which they put a calorimeter. So it's an oil-filled calorimeter, which means that it's at the refractive index of the oil. So they can get a concentration factor, which is N squared times the concentration factor without the oil. And they have thermocouples to measure the temperature. So it allows you to increase the concentration factor by a factor of N squared.
Dr. Menon, what happened to your audio?
Can you not hear me?
No.
Hello, hello, hello?
Hello, no, we cannot hear you.
I didn't change anything. That's weird. Let me see.
No, something happened. Can you?
I didn't change anything on my end. It's all the same. Is it still muffled or what's going on? Is it too soft?
It's a little better now.
Okay. Nothing changed on my end. Maybe check the cable for the HDMI. It's loose or something. In any case, so let's move on.
It's better now.
Okay. So at this point, I want to show a few examples, and then I'm going to wrap up, and so we're a little early, but I want you to spend the last 10 minutes or so, 15 minutes on the design problem that I'll pose. But so take the extra time to do the brainstorming, as well as let's meet with your team. So we'll talk briefly about the assignment too as well at this point. But let me show a few examples of where I'm going to show two different concentrator technologies. One extremely simple. So it's a very simple science demonstration of a tracking technology which could potentially be used for concentration. So let's look at that first. Okay, this is a very, very simple demo of a tracker that uses solar energy itself to actually do the tracking. So I'm gonna play this, and then I'd like you to think about how you might, for instance, improve upon this technology. Let's see if this will work. Oh, whoops! I think maybe there's some issue with my videos, so I'm gonna hold on a second. I'm gonna try to load this again. I had some issue with my flash earlier. Sorry about that. Okay. Let's see if this plays. Some issue here. Hold on. Okay, now it should play, hopefully. So I'm going to actually go through this fairly quickly, so we have time. So, of course, this is great because it was done by a elementary school or middle school's kid. So basically, there is a turntable, okay, and there's a solar panel, which is held, two solar cells, held at a V shape, and she has the turntable as the tracker, and there is a motor here, of course, that can be used to turn the turntable. And depending upon which way the light is shining on the solar cell, you can actually have the turntable travel in one clockwise direction or the counterclockwise direction. So basically, that's what she's demonstrating here. So by aligning that V shape directly to the solar cell, to the sun, you can essentially have the solar, this axis of this V groove essentially matched to the center of the solar cell. And she's just showing that by flipping the, the terminals. Of course, you can spin the motors in two directions. So she's relying on a balance between these two, shown here. The balance between the current produced by this solar cell and this solar cell to essentially match the axis of this concentrator to the center of the sun. So it's a very, very clever way to track, for instance, in this case, a parabolic concentrator without using any additional energy. I won't go through the details here, but there is one more. I'll post the link, so if anyone's interested, they can certainly go through it. But it's pretty cool because it's done by a kid, and it's a very elegant, simple idea. So essentially what they're showing is that it will always automatically align such that the intersection of these two solar panels will always align to the direction of the sun. This is, of course, what you're trying to do. So Okay, so that's one. I like that idea because it's very simple. So that's a more complicated concentrator comes from I'm going to actually play this one, is the heliostat. Okay, so we talked about how the heliostats concentrate light by following the sun. Now, the heliostat, of course, requires tracking. So in this example, they have a heliostat which is essentially tracking the sun similar to what plants like the sunflowers would do. So in this case, they in the sunflowers, for instance, use water, essentially pumped water, which allows the flower to follow the sun. So in this case, they have hydraulic system. So this is very interesting because it's a modular system. This is actually from
everyone wants solar energy to be cheap, but right now
so
it's
let
not.
it play.
And one of the reasons is for the
this is from a few years ago,
solar,
of course.
you basically have a robot that has to point these solar panels or these mirrors at the sun to very high accuracy. And when you do that with metal and motors, at some point it ends up that the solar, it's not really a good trade-off to do solar anymore because you're using so many resources and you're doing it so expensively. It's not really accessible to most of the world. So we're working on a new form of solar tracker that's based on plastic and water actuators as opposed to the traditional metal and motor-based actuators. This is the actuator we're basing our solar trackers on. We call them heliostats because they follow the sun. Over here we have a very small-scale version of our array. And our actual array would maybe have 100 mirrors this size. And these mirrors are much smaller than what's out in the field right now. And there's a lot of advantages to that. One of them is the closer you get to the ground, the less wind loading is a problem. And because it's so lightweight, we could start thinking about putting concentrated power on rooftops, places where we haven't been able to do it before because it's such a heavy system. One of the mirrors on this array is demonstrating movement. And the movement is happening just by distributing water to each of the chambers.
So here you can see you don't need big advantages. Of course, you don't need gears and motors and things like that. You still need the...
Instead of having a motor on each of these, instead you'll have a centralized control system that just routes the fluid where you want it. We have one small control system that can control up to 100 or more of these, and makes the cost of control very low. There's very few people doing robotics that is fluid-based, and definitely no one in the solar industry is doing hydraulics this way. Well, if everything's successful, we're introducing something that could make solar energy at coal parity cost. So solar power could actually be as cheap as any other form of energy, which would be very enabling.
And so there were two things I wanted to talk about. First of all, I want you to think about how, for instance, can you improve on this very simple idea of balancing two solar panels to track the sun. So that's number one I want you to brainstorm. And the second problem I want you to brainstorm, is can you design a concentrator that concentrates sunlight into a ring? Okay. Now let me explain why you may want to do that. So for instance, in one of the assignment presentations, we heard about the ZEER part, right? We had a ZEER part which was for solar cooling. In that case, you have a circular area in the center where you don't want to heat. That's where you want to cool. But you have a hot area which is shaped like a ring. So in that particular situation, the performance of the ZEER part can be improved if we could concentrate, for instance, sunlight into a ring. So I'm going to stop here and allow you to brainstorm for the rest of the class. I know we are a little bit early. So use the extra time to brainstorm with Apratim will lead the brainstorming session on this problem and improving the tracking system. And if there's any time left over, please meet with your teammates to discuss the assignment. If you're done with
your audio is... Sorry, go ahead.
Sorry, if you're done with those two activities, then you're welcome to leave early. I just want to also point out very quickly on the schedule that we are here. On Thursday, we'll talk about radiometry and photometry. And next week, we have the ray tracing software tutorial. So make sure you come with the console already installed or have access to console on your laptop so you can follow along. Okay? Now, and of course, then we have the midterm review. So be aware that we have the midterm on October 4th. I'm going to stop here and ask if there are any questions.
Have you posted the expectations for assignment 2?
Yes, so we can go through that. It was in the lecture notes here, actually. So they're already posted. I will repost it again so you can find it easier. Let me find it here. Oops, there we go. So this is roughly 2, 3, and 4. Okay, so you see number 2 is list the results of your brainstorming session for your project. I would present at least 3 crazy or novel ideas. Be creative here, but of course be wary of physics. Pick your top idea. If you have more than one, it's fine. And describe it in some detail. Explain why this is novel and what problem will this solve. Finally, present some preliminary calculations / simulation / analysis of your selected idea/ideas. Be as quantitative as you can, but you can leave the very detailed analysis for the next assignment. This is really like kind of, I want to get a sense for your brainstorming of how, remember in the last presentation, you actually identified problems, and now you're trying to brainstorm on how could you solve those problems. Okay. I'll post this this particular slide again on the top of the website, so you also have this separately. Any other questions? Okay, if not.